In this video, we're going to talk about static typing versus dynamic typing. One way to think about the purpose of static type systems is to prevent common programming errors. And they do this at compile time. So they do this when the program is compiled. And in particular, they do it without knowing any input to the program. So the only thing that is available is the program text. And that's why we call them static, because they don't involve any of the dynamic behavior, the actual execution behavior of the program. Now, any type system that is correct, any static type system that actually does the right thing, is going to have to disallow some correct programs. It can't reason completely precisely at compile time about everything that could happen when the program runs. Now, what this means is that some correct programs, by that I mean some programs that would actually run correctly if you executed them, are going to have to be disallowed by the type checker. And so for this reason, some people argue for dynamic type checking instead. And this is type checking that's done solely when the program runs. So at runtime, we check whether the actual operations we're executing are appropriate for the actual data that arises when the program executes. Other people say, well, the problem is really just that the type systems aren't expressive enough and that we should work on fancier static type checking systems. And over time, there's been considerable development in both camps. We see a lot of new dynamically checked languages coming out. So a lot of the modern scripting-like languages and domain-specific languages have some form of dynamic type checking. Other people have been working on fancier and fancier type systems, and actually there's been a lot of progress in static checking. The disadvantage of the more expressive static type checking systems is they do tend to get more complicated, though. And not all of these features that people have developed have actually found their way yet into mainstream languages. Now, one important idea that this discussion suggests is that there are two different notions of type. There is the dynamic type. That is the type that the object or the value that we're talking about actually has at runtime. And then there is the static type, which is the compile time notion, what the type checker knows about the object. And there is some relationship that has to exist between the static type and the dynamic type if the static type checker is to be correct. And this relationship can be formalized by some kind of a theorem that proves something like the following. What we'd like to know is that for every expression E, for every program expression E that you can write in the programming language, the static type that the compiler says that that expression is going to have is equal to the dynamic type of that expression. Another way of saying that is that if you actually run the program, then you get something that is consistent with what you expected to get from the static type checker, that the static type checker is actually able to correctly predict what values will arise at runtime. And in fact, in the early days of programming languages, these were exactly the kinds of theorems we had for the very simple type systems in the languages at that time. Now, the situation is a little more complicated for a language like COOL. So let's take a look at the execution of a typical COOL program. So here's a couple of classes, class A and a class B that inherits from A. So B is going to be a subtype of A, which we'll write like that. And now we have a declaration here of X having type A, and this is the static type of X. So the static type of X is A. All right, and that's what the compiler knows about X's value. And then here, when we execute this line of code, we can see that we assign a new A object to X. And the fact that it's new is not important. All that's important is the fact that it's an A object. And so at this point, the dynamic type of X is also A. Okay, so at this line of code, when it actually executes, A, which was declared to have static type A, actually holds an object of class A. But a little bit later on, down at this line of code, the dynamic type is actually different. The dynamic type here of X is going to be B. Okay, when this line of code executes, X holds a B object, even though it's declared to have a different type. And this is a very, very important distinction to keep in mind. So there's a static type, there's a type that the compiler knows about, and that's invariant. X has type A, it always has type A. All the uses of X for the entire scope of X are typed with class A by the compiler. In the last video, we talked about the difference between static and dynamic typing and how one trend in static typing is towards increasingly expressive type systems. In this lecture, we're going to talk about self-type, which will give you a taste of what those more expressive type systems can look like. To begin with, let's motivate the problem that self-type solves by looking at a simple class definition. So here we have a class count, and it has a single field I, which is an integer initialized to 0, and it has one method increment. And essentially, the class count just increments a counter. So initially, when you allocate a new count object, the counter is 0, and then every time you call inc, the counter's value is increased by 1. And notice that this can be thought of as a base class that provides counter functionality. So whenever I wanted a counter for some specific purpose, I could define a new subclass and that of count, and that subclass would automatically inherit the inc method, thereby allowing me to have counters without having to re-implement the code. And in this case, the amount of code is very, very small, but in general, you can imagine having a class that implements something tricky or requiring a lot of code, and it's useful to be able to reuse that in subclasses. Now consider a subclass of count that we might want to define called stock. Say we're implementing a warehouse accounting program and we want to keep track of the number of items that are in stock of certain different kinds. So we define a new class stock that inherits from count, and now we'll have a new field in here to make this object, this class, different from its parent. We'll just have a name that corresponds to the name of the item that's in stock. And now down here, we can actually use this. We can allocate a new stock object. So we create a new object. We increment it to indicate that we have one thing in stock, and then we assign it to some variable that we've declared of type stock. And then later on, we can use this A object as we like. Now, the problem is that this code actually will not type check. There is a type error in this code. And why is that? Well, let's think about it for a minute. So what is the signature of inc? So inc, remember, was declared to return things of type count. Right? And when the inc method is inherited by the stock class, this signature doesn't change. It still returns things of type count. So here we have a new stock object. We call the increment method, but the type of this whole thing is a count. And then we try to assign that to a stock, but that doesn't work because count is not a subtype of stock. A variable of type stock can't hold a value of type count. And so the type system will report an error right here at the assignment statement. And you can see that this is actually a serious problem because it's made the inheritance of the increment method pretty useless. I can define new subclasses of stock, but I can never use the increment method on them, at least not without getting back something of the parent type. And so it's not as, the inheritance of the increment method is not as useful as one might have hoped. So just to review, new stock, the incremented new stock will have dynamic type stock. That'll actually be a stock object that is returned. Okay, so don't get confused here. This is the dynamic type I'm talking about. So when we allocate the new stock object and then we call the increment method, remember the increment method returns self. So the increment method was implemented something like this. I'm going to leave out the types, but it was I gets I plus 1, and then it returned the self object. All right, so it's definitely returning whatever object is passed in here at the dispatch point. So it's returning something of dynamic type stock. And so this program will actually run, if you didn't have type checking, you could actually run this and it would work just fine. This would produce a dynamic stock object and it would store it into the stock variable. But it's not well typed because the type checker loses track of the fact that this is a stock object. All it knows is that increment is declared to have return type count. Which is certainly correct because every stock object is also a count object. It's just not useful in the context of this piece of code. And so the type checker loses information, which makes it not very pleasant to try to put the increment method in the count class to begin with. So to solve this problem, we're going to look at extending the type. In this video, we're going to continue our discussion of self-type by talking about the type-level operations that are available on self-type. And this will help to clarify what self-type actually is and its role in the type system. So let's begin by thinking about the example that we discussed last time. And if you've forgotten what that is, let me just write it down quickly. We had a class called count. And count had one field, an integer I, that was initialized to 0. And it had one method called inc that returned something of type self-type. And all inc did was to increment the counter field and return the self object. And I've probably made some syntax errors here, but that's not really important. That's the basic code for the count class. And the question is, what can be the dynamic type of the object that's actually returned by inc? And the answer here is that it could be whatever is the type of the self object, whatever is the dynamic type of the self object. And if we think about a big program where there's multiple classes that inherit from count, then the answer is that inc could return count or any subclass of count. So it's going to return something that's at least, at most count, but it could return something more specific. The dynamic type could be something more specific. It could be a subclass of count or a subclass of a subclass of count. Anything that inherits directly or indirectly from count is a possibility. So what's the general case? Well, let's think about a class C. And in this class C, there's some expression buried somewhere inside of it that has the type self-type. And it doesn't really matter how that expression got the type self-type or what it is. Let's just say that it has that type somehow. Well, what are the possible dynamic types of the expression E? And from our discussion on the previous slide, it seems clear that the dynamic type of E, when you run E, you're going to get back something that's a subtype of the class C, the enclosing class in which the self-type appears. And that's interesting because it shows us that the meaning of self-type actually depends on the context. So what this self-type means a subtype of the class C. If I had written self-type in a class D, somewhere in the definition of class D, there it would mean a subtype of the class D. And so to remind ourselves what class we're talking about, what enclosing class we're talking about, we're going to subscript occurrences of self-type with a class name. So self-type sub C here is going to refer to a syntactic occurrence of the keyword self-type in the body of the class C. And this also suggests a very simple typing rule, and really the first useful fact about self-type, which is that self-type sub C is a subtype of C. And this is really a key idea here, that a self-type in class C is some subtype of the class C, because this also helps illustrate what self-type really is. The best way to think of an occurrence of self-type is that it's a type variable that ranges over all the subclasses of the class in which it appears. So self-type sub C you should think of as a type variable. It's something, it doesn't have a fixed type, but it's guaranteed to be some type bounded by C. So it's going to be only one of the classes that inherits directly or indirectly from the class C. Now that rule, that self-type sub C is a subtype of the class C, has an important consequence. It means that when we're doing type checking with self-type, it is always safe to replace self-type sub C by C. So it's okay to promote any self-type sub C, which could be C or a subtype of C, to just say, okay, we're just going to say that it's C. All right. And that suggests one way to handle self-type, which is just to replace all the occurrences of self-type sub C by C. Now, unfortunately, that turns out not to be very useful. It's sound, it's correct to do that, but that's really just like not having self-type at all. That's as if we went back to the example we did in the last video where we started out without self-type and we found out we couldn't use inheritance in the way we expected. So to do better than just throwing all the self-types away, we need to incorporate self-type into the type system. And the way we're going to do that is by looking at the operations that work on types in the type system, and there are two of them. Now that we've seen some of the operations on self-type, in this video we're going to talk about where self-type can be used in COOL. The parser checks that self-type appears only where types are permitted, but that's in fact a little bit too permissive. There are places where some other types can appear, but self-type cannot. And so the purpose of this particular video is to go over the various rules for the usage of self-type. So let's begin with a very simple rule. So self-type is not a class name, and so it can't appear in a class definition. It can neither be the name of the class nor the class that is inherited from. In attribute declarations, the type of an attribute, in this case we have an attribute X and it's declared to have type T, it is okay for T to be self-type. So it's fine to have attributes that are declared to be the self-type of the class. Similarly, it's fine to have local let-bound variables that have type self-type. And it's fine to allocate a new object of type self-type. And what this actually does is that it allocates an object that has the same dynamic type as the self object. So whatever the type of the self object happens to be, which is not necessarily the type of the enclosing class at runtime, the new T operation will create a new object of that dynamic type. The type named in a static dispatch cannot be self-type, again because it has to be an actual class name. Finally, let's consider method definitions. So here's a very simple method definition. It has one formal parameter x of type t, and the method returns something of type t prime. And it turns out that only t prime, only the return type, can be of type self-type. No argument type can be of type self-type. And to see why, I can show it actually two different ways why this has to be the case. And we'll do both because this is actually important. So let's think about a dispatch to this method. So let's say we have some expression e, and we call method m, and we have some argument e prime. And now let's say that the argument e prime has the type t0. So if you recall the rule for method calls, t0 is going to have to be a subtype of the type of the formal parameter. We're going to be passing this in. And so whatever type x is declared to have here has to be a supertype of the type of the actual argument. So that means that t0 is going to have to be a subtype of, and now let's assume that the argument can be of type self-type. So it would be that the t0 has to be a subtype of self-type, and this is in some class C wherever this method is defined. And remember that we said this was always false, that you couldn't have self-type on the right-hand side and a regular type on the left-hand side, because that would lead to problems. That we would never be able to prove that in general for that a type is actually a subtype of self-type, because self-type can vary over all the subtypes of the class C. So that's one way to see that we can't allow method parameters to be type self-type. But it's also helpful to just think about executing the code or some example code and see what can go wrong. So here's an example, and let me just walk you through what happens if we allow a parameter to have type self-type in this particular example. So there are two class definitions. Class A has a method comp for comparison, and it takes one argument of type self-type, and it returns a bool. So the idea here is that the comparison operation probably compares this parameter with the argument and returns true or false. Then there's a second class B, and B is a subtype of A. It inherits from A, and it has one new field, B, little b here of type int. And now the comparison function in class B is overridden. It has the same signature as the comparison function or the comp function in class A, but the method body here accesses the field B. And now let's take a look at what happens with a piece of code that uses these two classes. So here, x is going to be declared to be of type A, but we're going to assign it something of type B. And here notice that there's a gap between the static type, which will be A, and the dynamic type, which will be B, and that's actually key to the problem. And now In this video, we're going to use what we've learned so far about self-type to incorporate self-type into the type-checking rules for COOL. First, let's remind ourselves what the type-checking rules for COOL actually prove. So the sentences in the type logic look like this, and they prove things of the form that some expression has some type, and they do that under the assumption that object identifiers have some types given by O, methods have signatures given by M, and the enclosing class, the current class in which E sits, in which we're doing our type checking, is class C. And the whole reason for this additional piece here, we haven't actually discussed this before, why we needed this C, it is because self-type's meaning depends on the enclosing class. So if you recall that we introduced this notation, self-type sub C, to record in what class a particular occurrence of self-type sits, and this C in the environment is exactly that subscript. It is tracking what class we are in, so when we see an occurrence of self-type, we know what kind of self-type we're talking about. So now we're ready to actually give the type rules that use self-type, and for the most part this is really easy because the rules just remain the same. That is, they look the same, but they're actually a little bit different because they use the new subtyping and least upper bound operations that we defined before. So for example, here is the rule for assignment, and this looks identical to the rule for assignment that we discussed several videos ago. But notice that this use of subtyping here is now the extended definition of subtyping to incorporate self-type, and so now this rule works with self-type as well as with the normal class names. Now, there are some rules that have to change in the presence of self-type, and in particular, the dispatch rules need to be updated. So here is the old rule for dynamic dispatch, and this rule, this part of the rule, actually doesn't change. It stays the same. But I just want to point out the essential restriction in this rule is that the return type of the method could not be self-type. And that's actually the place where self-type buys us something. So the whole purpose of having self-type is to have methods whose return type is self-type, because that's where we actually get the extra expressive power. And now we have to consider the case, now that we have self-type and we've done all this work, what if the method's return type is self-type? How are we going to type check that? Well, here's the rule. So as usual, we type check the expression that we're dispatching to, that's E0, and all of the arguments, and we just get their types. And they're just type checked in the same environment as the entire expression. And now, just like before, we look up in class T0, the type of E0, the method f, and we get its signature. Okay? And then we have to check that the arguments conform, that every actual argument, E1 through En, has a type that's compatible with the corresponding formal parameter in the method signature. And if all of that works out, then we can say that this dispatch is going to have type, oh look, T0. So where did that come from? Well, the return type is self-type, and so the result of this entire dispatch is going to be the type of whatever E0 was. E0 is the self parameter, and whatever type we got for E0, that is a sound static type for the result of the entire expression. So we simply use the type of E0 as the type of the entire the entire dynamic dispatch. Now recall, the formal parameters of a function cannot have type self-type, but the actual arguments can have type self-type, and the extended subtyping relationship will handle that case just fine. One interesting detail is that the dispatch expression itself could have a type self-type. And so what do I mean by that? Well, let's think about E0 dispatching to method f. And then what happens if E0 has type self-type? What if we can prove that E0 has type self-type? And the problem here is that we need to look up in the M environment, in the method environment, in some class, the definition of, or the signature of method f. We have to get back that type signature so that we can do the rest of the type checking. And if E0 has type self-type, normally we use the type of E0 to do that lookup. What type do we use here? Well, if this whole thing is occurring in class C, if we're typing, In this video, we're going to wrap up our series on type checking with a discussion of how to recover from type errors. So as with all the other front-end phases, like lexing and parsing, it's important to recover from errors that happen during type checking. But unlike parsing, it's much easier to recover from errors in the type checker because we already have the abstract syntax tree. And so there's no need to skip over portions of the code as we did in parsing before we even knew what the structure of the program was. The problem, though, is what type should we assign to an expression that has no legitimate type? The type checker works by structural induction, and it can't just get stuck. So if we find some sub-expression that has no type that we can meaningfully give it, we still have to do something with it so that we can type check all the expressions that surround it. One possibility is to simply assign the type object as the type of any ill-typed expression. And the intuition here is that even if we couldn't figure out what the type of the expression was supposed to be, certainly it was something that was a subtype of object, and so it is certainly safe to assign any expression the type object. So let's consider what happens with this strategy in a simple piece of code. So here we have a little code fragment, and we'll just assume here that x is undefined, that actually there's a bug in this code, and that's that x has no binding, so there's no type anywhere for x. So what happens when we type check this? Well, we're going to recursively walk down the abstract syntax tree. Eventually we'll get to the leaves, and we'll try to type check x, and then we'll discover that there is no type for x anywhere. And that will result in an error message saying that x is undefined. And then in order to proceed with type checking, in order to recover, we'll have to assign x a type. And so we'll just assume that x has type object because that's our recovery strategy. And now we'll continue to type check as we walk up the abstract syntax tree, and the next thing we'll try to do is a type check this plus operation. And we'll see that we're adding something of type object to an integer. And of course, plus doesn't work on things of type object. So we'll get an error, something like plus applied to an object. And then we'll have to decide, now that we couldn't type check this plus, what the type is of x plus 2, so this whole sub-expression. And of course, our recovery strategy is to say, well, that also has type object. And now the next thing up in the abstract syntax tree is this initialization assignment. Here we're assigning y the result of this expression, but we couldn't type check this expression, so it has type object. And now the type checker sees that we're assigning something of type object to something of type int, and we get yet a third error saying that we have a bad assignment of some kind. So the nut of the problem here is that this simple recovery strategy works. We do recover, we continue type checking, but a single error leads potentially to lots of other errors. So this is a workable solution. It achieves the goal of recovering, but in general it will lead to cascading errors. Once you have one type error, that type error will just cause many more because not very many things can be done with something of type object, and probably the code was written assuming some more specific type. And these errors will just propagate up the abstract syntax tree until some point, and it just result in multiple errors. Another possibility is to introduce a new type, no type, that is specifically for use with ill-typed expressions. And no type is very special. It's not a type that's available to the programmer. It's only available to the compiler, and it's just there for error recovery and type checking. And the special property of no type is that it's going to be a subtype of every other type. So if you remember, object was the opposite. Object is a supertype of every type, and that had the bad property that there are very few methods defined on object, and so if you plug in type object where you expected some other type, probably it's not going to type check. So we can fix that problem by introducing no type, and no type will have the special property that every operation is defined for no type, and furthermore, we'll say that it produces no type as a result. So any operation in the language that takes an argument of type no type, it will produce a result of type no type. So the no types will propagate. And now let's take a look at our same code fragment, and let's work through what happens if we use no type. So again, we walk